Today we're going to look at some more fundamental concepts and programming structures. As you can see here, I got a text which is from Wikipedia, and it's basically an article about cheese. So I went to Wikipedia, looked for some nice test input for my tutorial, and thought, why not use cheese as a funny example? So what we want to do is we want to process this text that we take, for example, from the internet, and we want to calculate some statistics about the text content. We will mostly count words, and that is a very practical example for an introduction to some more basic data structures. In particular, we're going to talk about lists, which are called slices in Golang, and we're going to talk about maps, which are the other fundamental container type in Golang and also in other programming languages. What will the program look like when we're done? Just to get an idea, I'm going to show it. We will write a little program that we can run with our Go tool, and it's going to read my text file, input text, and then print some statistics. So of course Go is not complete. We need to call Go run, give it the main file containing the main function, and then you can see I get a nice listing of all the words from the text. And in the first column you can see the count, and in the second column the word, and it's actually sorted. So right at the bottom we got the words which are most common in the text. Of course cheese is pretty popular in this text, and also some common words like the, and, of, and so on. But also milk, for example, or something like produced, or cheese making, or fat. I'm also printing the unique word count. So when you count every word once from this list, you get the unique word count. So 1806 distinct words. And when you count the duplicates too, you get the total word count, like total text length. We're also going to have a look at a bit of efficiency perspective for data structures and programming. That's why I print the processing duration here. And we're going to add a function where you can look up the count of a word. So for example, I can get the count for milk. I enter milk, press enter, and the program looks up the count, which is coincidentally 42. Maybe you know that 42 is basically the answer to the question of everything. And when I enter a word that is actually not in there, like let's say alien, I'm pretty sure it's not in there, we get the default of 0, which seems correct. Okay, so that's what we are going to build. Moreover, let's have a little look at the technical content, so you know what you can expect of this video. At first, we're going to learn how to read text from a file, and we are going to split it into words because we want to count words, so we need to separate it into words. I'm going to give you an introduction to slices, which are basically list structures. And slices are a special version of lists in Golang that are more powerful than lists from a lot of other languages. We're going to learn about the basic features of slices. We're going to count the total number of words, which is basically explaining the lang function. We're going to read text from the terminal. This is what I've shown you when I enter the word to look for. We're going to determine the count of specific words by searching. So we're going to learn how to do a simple search in a list of values. We're going to do some string work like normalizing strings, cleaning up them. There are commas and dots in there, and we need to remove them for clean counting. I'm going to give you a minimal introduction to structs, which are a data structure type. And we're going to count occurrences per word in a simple but naive search approach, which is nice to know but not very efficient. Then we're going to sort elements in the list. And finally, to make things more simple and efficient, I'm going to introduce the concept of maps and how we can use them for an efficient lookup approach. We will see how this refers to the processing time by doing some basic time measuring. So that's it. That's what we're going to handle in this tutorial. And if you find anything of it useful, feel free to leave a comment, like, subscribe, or if you think that just part of it is interesting for you, then feel free to use the text in the description to jump to the locations that you're interested in. Let me start by referring to the go.dev website. If you didn't install Go yet, please have a look at the Get Started documentation, where you can find a description on how to install it depending on your operating system. Or have a look at my first tutorial where I explained a little bit more about where to find installation instructions. I'm using Visual Studio Code for this tutorial. You can use whatever editor you like. I recommend to practice what you learn here. You can do that along to the video, or you can pause the tutorial at any point and try it yourself, or do it after watching, whatever you like. Now, when we go to the terminal, we need to create a directory for our project, which is located in our usual Go path. Again, if you don't know about it yet, please read the documentation about it. And I already created a directory. I call the project text -stats. And there's not much in here. I created my README file that's just a guideline for our progress in this project, and an empty main.go file, which shall be our source code file. And that's where we start. So, as you probably already know, we need to declare a package. I'm just going to call it main. And we will start with a simple print statement. I'm going to import the standard package fmt for formatted out and input. and write the main function, which is called main, and the entry point for our program. The body is enclosed in braces, and I'm going to print hello world for testing. Now save and go back to the terminal. And run the program. Go run main.go and you get hello world. Okay, so let's actually start with some content. We're going to start by reading text and splitting it into words. I already mentioned the Wikipedia example text. So let's create a file. I'm going to call it input.txt. And we copy our test text to it. So that's what we use for testing. So you can take another text if you want to. Just make sure it's a little bit longer and not too short. So we can actually test some counting operations later. I'm just going to copy that and thank God there's Wikipedia, which gives us a lot of free access to information. And I can copy that to my file for testing purposes. So I open input txt, paste the text, and you can see there's quite some text in there. Of course, a lot of blank lines, some numbers. We will handle these in the course of the tutorial. Then save the input. And now we need to learn about how to read this. Now, as always, the documentation is your friend. So, for example, you can go to go.dev or directly to packages.go.dev and search for packages. I already did that, and in the OS package you can find basic operating system examples. There's an example for opening files for reading, and you can see how it works in a very simple and readable way. But I'm going to show you in the code, of course. So first we need to import the standard package OS to actually use this function. If you're using rather smart IDE like VS Code, you should even be able to see some auto completion here. For some reason it's not active in my case, but we can fix that. So as you can see in the documentation, there's a simple version of the function called just open, where you pass the name of the file. And this is the return value. You get a file pointer to be specific. Pointers are something I'm going to discuss in a later video. For now, just assume it's a file that is returned. And an error, you can check the error for strange results, like when the file could not be read for some reason, or there was another error, then this return value will contain an error and not a nil, which basically indicates everything went fine. So let's try this. We're going to pass the file name. We are running it from the same directory as the file, so we can just write input Text. We get two return values. That's why we need to assign two variables. The first is the file. I'm just going to call it file. The second one, separated by comma, is a potential error. Usually it's called error. We're going to declare and assign both variables. So remember the colon assignment operator for declaration and initialization. So that's what you can do in Go. Some languages don't have that, but Go supports multiple return values. And they are just listed from left to right, separated by commas. Now it's a good practice to check if an error happened. Every function that may return an error should receive some kind of error handling. So we're going to check if error is not nil. Nil is the value for nothing, and it means there is no error. So if there is an error, it's not nil. That's exclamation mark, assignment or equals sign, which means not equal to. So we check for potential errors. If there is an error, what do we want to do? We can't actually work with the file when there's an error because the file might not exist or it might be broken or something like that. So what we do instead is we're going to print a message so that we know there was an error. Printf is a good candidate because we can say error on reading file, and then we're going to include an error description. Remember the placeholders, which are introduced by the percent sign, and v is a placeholder, %v, for the default format, which is fine in most cases. In this case, we are passing an error value, and Go knows how to print an error value in a default format, so you don't have to worry too much about it and can just write %v. So that's what we're going to do, and we're going to exit the program. That's what we can do by using os.exit, and we're going to pass, let's say, 1 as an error code to indicate something went wrong. Because we're going to do something with the file here, we don't want to continue the program if we didn't read the file successfully. So that's why I'm calling os.exit here. We could also use an else statement, but that leads to eventually to very deep nesting, and such an early return or early exit can be helpful to make error handling more clean. So actually, before we test the success case, it's also important to test the error cases. So I'm going to write unknown.txt, and let's see what happens. Go run main.go. And at first I'm going to get an error, file declared but not used. That's the compiler telling me I'm not using file, so I shouldn't declare it. The variable file, not the string word. That's pretty strict, but also a good idea to keep a code clean. What we can do in this case is to use the underscore placeholder, which is basically a variable that doesn't really exist. So it means ignore this return value. We don't want to use it, so I don't need a variable. It's just an empty placeholder. And save, and that should work. As you can see, we go into the if branch, error on reading file, open unknown, no such file or directory. Exit status 1. Okay. So that's it. We tested our error case. Now let's go to the success case. Actually, I'm going to add the line break here so that looks a little cleaner with the error message. Let's handle the happy case, as you might say. We're going to reintroduce our file variable, and we are going to print the content just to make sure we got the reading of the file right. So this is a file, a pointer to a file, which is basically a descriptor to the file. And now we need to find a way to get the text out of it. We need to find a way to actually get the content of the file, because this is just a pointer to it, or a descriptor, as you might say. We're going to use another standard library package, which is called buff.io. It stands for buffered input output. And when working with data, for example from files, this is a common thing to do also in other programming languages. The text can be quite big, or the data stream, so you want to use a buffered version and not load too much in one chunk into memory, because it could take up a lot of space in your main memory. What we need to do here is to create a reader. A reader is a basic abstraction in Go, and it basically means it's something that can read data. The specific implementation may use a file, it may use your terminal input, it may read something from the internet. There are very different implementations, but there are common operations that you can define on them. So we want to get a buffered reader, and we do that by providing a basic reader. And as the documentation says, it's going to use a default size, which is fine for us. Luckily for us, file is already of type reader. You can see that in the when you dig deeper into the implementation, that file is also a reader, or find some examples about it. And we basically just wrap it in this buffered reader. So let's call this reader. And the next thing we're going to use is a scanner. So the scanner is actually responsible for reading the content. So it accepts the reader, and you can specify split functions to use for the scanner to scan individual parts of the input. And you can do that by calling the split function. But for now, let's just use the default. and see what happens. The scanner offers some functions to call, and the most important function is scan. As you can see, it returns a Boolean. The Boolean says if the next part could be read or not. So the documentation confirms that. It goes to the next token. In our case, this can be a word later. And if it successfully read the token, it will return true. If there is an error, or if we have reached the end of the input, it will return false. So let's just do this once. We're going to call scan, and we assign a variable success to check if it actually worked. So if success, we can call the text function. Bytes would get us the binary representation, what we are going to call text, and that's returning the string token that has been read. And we can immediately print it to the terminal. If it is a failure, no success, we're going to print an error and exit the program. Let's try this. Save and run. And as you can see, it actually read the first word of the file. Or I guess it's the first line. So let's check if this is correct. First line is the caption. Just for testing, we're going to write some more words here, save it, and see what happens. Yeah, we're getting the first line here on our first read. That means by default, the scanner is splitting line-wise. So if you don't tell the scanner where to cut a token, it does it between lines. So a line separator like \n on Linux, Mac, or carriage return line feed on Windows will be a separator for the scanner. Now what we actually want is to separate words. Luckily for us, there's already a split function. We can say split, which configures the split function. And then we look into buff.io and we can say scan words instead of scan lines. Scan lines is a default, it's a function, standard function for this purpose. And we can say scan words. So sets the split function for the scanner, default is scan lines, and we do scan words. So let's see what happens now. Guess, yeah, one word is one token and they get the first word only, even though we added some more words here. So I'm going to remove it to get the original article. And now, as you can see, we need to do this for every word. So that's where we get back to loops. If you don't know what loops are, please have a look at my first tutorial video where I explain them. What I'm going to introduce to you now is the concept of a list or a slice. So we could do the following. We could say, as long as scanner returns success, So for scanner.scan, as long as it returns true, is basically successful reading a word. We print the word and go to a new line. And once it's no longer successful, we don't do anything anymore. So let's see what happens. Don't forget to save. And you can see it's printing every word line by line. So that's nice, but we actually want to hold all these words in memory. We don't only want to print them, we want to store them in variables and do something with it, like counting occurrences. And that is where slices come in. Just a quick recap. We opened a file by using os.open. This opens the file for reading. Writing is a different story. We check for errors. We wrap the file reader in a buffered reader, which is typical for reading files or other data, which can become quite large. And we pass it to a scanner, which does the job for us of reading individual lines or words. In our case, we can do that by using split. So now we can move on to slices or lists. When we talk about lists, we are actually talking about data structure that most of us are very familiar with. You can see a simple illustration here, and a list is what you already know from your shopping list or maybe your phone book or list of to-do items that you want to do in a given day. It's basically just a sequence of elements, and these elements are given in a specific order. So the order is static and sometimes important, and I can enumerate every element in the list by a number. While we usually start at 1 in our everyday life, most programming languages start at 0. And that's also how it's done in Golang. So the first element of a list, cheese in my example as a word, is located at index 0. And then more elements with an index that is 1 larger than the previous one. The index is quite important for the concept of lists or slices. I also talked about arrays in my first tutorial video, and you can immediately see the similarities with arrays. Using this illustration here, you could also say it's just a basic array. The only difference is that lists or slices, as they are called in Golang, are a little bit more flexible and a little bit smarter kind of a data structure. So while an array has a fixed size of maybe 6 elements, like we see here, a list can grow its size. So let's assume we need another element in this list, and we want to add maybe the word production. So in a list structure, I can just append it at the end. This is what we call an append. And it's added to the end of the list at the next index. I could also remove items. I could say I want to cut the elements at index 2 and 3 out of the list. And that's actually where slices shine in Golang. You can basically slice it out, remove it, and then we got a list like cheese, milk, music, food, production. Of course, the indexes change accordingly, and the size changed too. So our previous size was the length of the list, which is the number of elements in it. These are 7 elements indexed from 0 to length minus 1. So length is 7. Now we remove 2 elements, and now we got 5 items. So the length is 5. Very simple, right? So that's the gist of it. Lists are very handy when you want to store a sequence of elements. So they have a specific order. Can list them as cons here. Holds a sequence of elements. It has a specific order. This can be useful, e.g. if you need sorted elements. And you're pretty flexible. You have some flexibility of adding or removing elements. There are quite a lot of situations where you don't want to hold a lot of elements, each in individual variables, but instead they are similar and you can hold them in one variable, which is a list in this case. So these are the pros. We will get to the cons later, at a later point. And just as a heads up, of course, there are always pros and cons to each concept and data structure. So there are situations where it's very practical to use them, and other situations where maybe another concept might be more useful for your goals. So just to talk shortly about the difference between lists and slices. List is basically the general concept that we know from our daily lives, and a lot of programming languages have list types. In Go, it's mostly about the slice type, and that is because it's more flexible than most simple list implementations in other programming languages. With slices, you can do things like cut certain regions from a slice, like you can say, I want to pick this range from 2 to 4 exclusive, so 2 to 3, and you can basically extract another slice. That's like having a different view on base slice as a new slice, like just this part of the original slice, which can be pretty useful in some cases. And of course, these would have new indexes 0 and 1. And basically they are built on top of arrays. So when you know a little bit about arrays, that's good, that's helpful. And that's the very fundamental data structure that slices are built on top of. For your daily programming work, you mostly don't need that information, but it's useful and interesting to know that it's built on arrays. And of course, the big difference to arrays is that slices or lists can grow pretty easily. And when you have an array, you need to make sure that you always have enough space. So under the hood, the language manages it for us, and it makes sure that a new underlying array is located when we need more space and the array is not big enough. So at the creation phase, we will see that later, you can specify how much space you need if you know it. If you don't know it at that point, it's not too bad. The underlying array and therefore the slice will grow as you need it. We previously read all words from the input file and printed each word in a separate line. Now, as you know, we want to analyze all words, so it's pretty helpful to store them in a slice or in a variable. So first thing that we're going to do is we're going to create a slice. I'm going to do it in an explicit fashion for the beginning, and we're going to call it words because we will store all words in there. So I use a var keyword for creating a variable, the name, and then now the type. The type looks like this. Slice is specified by this pair of brackets followed by the type of the element. So we can store any type inside a slice. Could be a basic type like an integer or a string or something else, or a more complicated type. We could even store a slice in a slice, so it's nested, but that's a little bit more complicated and we don't need it here, so we're going to start out with string elements. And now that's just the variable. We actually need to make sure that there's something that something is created where we can put the elements. And this is where the keyword or built-in function, let's say make, comes in. Make is a handy built-in function that you can use to create initial data structures like this. There are basically 3 data structures in Golang that can be created with make: slices, maps, and channels. We will discuss maps later in this tutorial and channels at a later point. But for now, you just need to know that make basically creates a new slice for us. And in order to do that, it needs the type. So I'm going to write type slice with element string. And the second parameter is the initial size. So if we want to create an empty slice, we can just pass 0. If we know, okay, we need X element spaces, we can give it the size and it will create and allocate memory. So it will request memory from the operating system for each of these elements. This can be helpful if you want to optimize performance and things like that. Just for illustration purposes, we're going to start with 0, especially since we don't really know how many words are in this text. So there's one more thing, and this is the compile time error here. Let's see what the Go command says. It says syntax error, unexpected, expecting equals. And if you paid attention to my last tutorial, you know it's because I used the shorthand declaration and initialization operator, which is not correct at this place because we don't initialize it here. We just declared the variable on the left hand side and now allocated space for it. That's what make does. And now we can actually start adding things to the slice. But first, just to make sure, we're going to print the initial state. So initial slice, I'm going to use the generic placeholder again. And you can do that with slices too, as you can see. Passwords. Of course, we have to use printf. That's why I get an underlining. New line. And now we can have a look. Actually, I have to scroll at the top. Oh, that's a long way, all these words. Hold on, we almost got it. Oh, no, we didn't. It's too much for my terminal. So what we're going to do instead, we're going to put this in comments so we can actually see what is printed at the beginning. And as you can see, the initial slice is empty. So the brackets are the placeholders beginning and end of the slice, and there's no element in there. Let's remove the hello world. We don't need it anymore. And now we got our code that is printing each word, and instead of printing, we want to add the word to our list. And that's where the built-in function append comes in. I can call append. As you can see here, the help documentation says this is the slice that I want to append to, the first parameter, and then I can add elements. These dots mean I can pass multiple of them. You can just specify them one after the other with a comma. And it appends elements to the end of the slice. It talks about the capacity. That's basically the size of the underlying array that we can specify also during make, but that's a little bit more complicated. We're going to talk about it another time. You basically just have to remember append is for adding an element at the end. And you have to assign the new modified slice anyway. So what we do here is we pass the slice at the first and then the element which comes from scanner.text. That's what's documented here. Append returns the updated slice. It is therefore necessary to store the result of append, often in the variable holding the slice itself. So that's it. We append. And now we're going to print it afterwards. So filled slice. Let's see what happens. And you can see there's quite much in there. Every element is separated by a space, so that's a little bit hard to see here. But there's the end placeholder of the slice. It's just to give you an idea. So that's how you do it with append. Now, if you know at what index you want to assign an element, we can explicitly read or write this element by using the bracket notation that you may know from arrays. So let's say I want to put or replace the last element. What I would do is I would say words and now the index. We don't know it from the top of our head, but we can calculate it with the lang function. This is another built-in which returns the number of elements. And we say length of words -1 because we start at index 0 and the last element is length -1. And then we assign our value. I will just call it replaced in uppercase so we can easily see it. Let's see what happens. Yeah, it actually shows the last element is our replaced element. And what we can also do is we can read elements, or we can say if the previous element is milk, we do something. I could say, okay, if words from length -2 equals milk, then I can print found milk as the almost last element. And let's remove this so we can actually see something. Found milk as the previous element of the last element. Okay. So going back to our illustration, addressing individual elements for reading and writing, you can just use the index and the bracket notation. It's very similar, basically the same as it is for arrays. Just make sure you are referring to elements that actually exist. So when I say length of words, this is an index that doesn't exist. It's one too many. We are above, beyond the size. So I will get a famous error if I do that. And that's basically a runtime error, index out of range. The program panics because it doesn't know what to do. There's no element. And that's a typical beginner mistake. But also seasoned programmers might make this mistake from time to time in more complicated scenarios. In some languages it's an array index out of bounds exception or something else that is indicating this issue. So the upper bound is the length -1 in terms of index, and on the lower bound we can't go into the negative scale. We can read and assign element 0, that's the first one, but as soon as you try to pass a negative value, you see even the compiler says it's not allowed here. So the compiler is even smart enough to tell us this is not possible. But maybe you have some more complicated program logic where it's not immediately visible that you are in the negative range. I'm just simulating this by using a variable. you know, there could happen some other stuff here, some other logic that leads to a negative index, and then you get the same error from the other direction, index out of range. That's about indexes. Append always adds at the end. And now just to make it a little bit more complete, I can show you a little bit of the powerful things of Go slices, and that is slicing elements inside the slice. And that's basically how you create a new slice that is a view on the old slice. So let's remove this and let's look at our output. We got, let's print it again. The last 5 elements are beverage, preparation, sheep milk, and cheese. Let's say we want to have another slice that contains this sub-slice, as you might say. We can easily do that with Golang's slice features. Now, a simple implementation of this, also from other languages, would be to create a new slice, right? So let's do this just for illustration purposes. Actually, I'm going to write a new function and we call this sub slice. We give it a string slice of words and we tell it from which index we want to start and end. Both are of type int. So let me just fix the order here. Let's parameter name first, type second. And our return value is another slice, so string. Given what we've learned so far and using loops, we can do the following. We can say, okay, my result slice is another slice, and we know it will have a very specific size, so we could even say the size is end minus start, because how are we going to call it for the last 5 elements? We are going to pass words, then let's specify the end first. The end is the length of the slice. Now, why the length and not -1? Because we refer to a standard that says the end is exclusive. So start is Golang inclusive and end is exclusive. And we start at length of words -5, I guess. We're going to test it, of course. So -5, 4, 3, 2, 1. And these are 5 elements. And now we can calculate the size. So the size that we need is an integer. It's end exclusive minus start inclusive. So we can say, I'm just going to print it, need slice of size this. Let's just do it like this. You can concatenate strings by using the plus operator with strings. You just have to make sure that actually all elements, all parts that you want to concatenate are strings. So here the compiler says, cannot convert it. What we can do is convert this value. This is called a cast. We specify the type and the parentheses to convert it, and for basic types Go knows how to do that. So now this is a string and this is a string, and the compiler can actually do something with it. When it's two different types, it doesn't know what to do because println wants a unique type. So now we just have to say how big this slice is, its size. And now we can use our loop. It's a classic loop. We start at 0 and end at length -1. We can actually say that we use the size variable because that is our length. And now I can directly assign the values. But what we're missing is the current position in the source slice. So I need another variable, which is the source index, and it starts at start inclusive. And of course, after each run, we need to increment it. And now we can say result index starting at 0, assign our source slice at position source index. So element 0, 1, 2, 3, 4 will be assigned the values from length -5, -4, 3, 2, and 1. And then we can return it. And oh, it's actually I shouldn't use the cast here. Instead, we should use the formatted printing function. D for decimal size. What you could do instead, you could use the plus operator for concatenating, but then we would need to make a string out of this here. You can do that by passing the variable as print formats using the default format and so on. But it's for printing debug output, it's easier to pass the variable with a formatter. So now to recap, we calculated the size, we created a new slice with the size of our subslice, and we iterate through our new slice indexes and the old slice indexes. Of course, you have to take care that you're at the right position and inside its bounds. So let's see if we did a mistake. And Of course, we have to assign the new slice and print it, otherwise we're going to see the old slice. So, need slice of size 5. Subslice is beverage, preparation, sheep milk, cheese. So these are the last 5 elements here. So that's handy to understand how indexing works and how you can create new slices, maybe with a given size. We could also say, okay, we don't care about the specific size, we want to keep it simple. Then I can just say it's I have to pass 0. And we drop this and we just say, okay, keep it simple. We run from start inclusive until we are at smaller than end exclusive. So smaller than. And we just say, okay, keep it simple. Result append our new or our sub element. So words from index. We don't need the sourcing. So that is already much simpler, right? So for that specific purpose, I would probably not write that complicated. Let's see if it still works. Yeah. So that's good enough. But given Golang's slice operations, we can make it even more short. We don't need to write such a function. We can actually say, okay, take my slice and I want a sub slice of that from start to end. So from lang words to -5, sorry, to lang words. And that's done by using this colon. You can say, okay, I want a sub slice. Yeah, let's just ignore this for now and see if that works. I can already delete this function. You can already see it's much simpler to do it like that. Once you wrap your head around it, it's very simple. And you don't have this in a lot of other languages. Some have it, but most don't. So you can use that to your advantage. Now, what does the warning say? The warning says we can even simplify it. We can say unneeded length word, so we can even remove this and implicitly keep the colon operator. That's important because otherwise it will address a single index. Colon, and then nothing means until the end. So it's like this. And the other way around, I could say, okay, from the beginning, I leave that empty left of the colon until element 3. Then we get the first 3 element. These are cheese from Wikipedia. Yeah. So that's pretty handy. Now we learned the basics about slices. Let me just give you another very basic simplification. We can, of course, use the shorthand for declaration and initialization. So Go already finds out about the type due to the right side of the statement. And see, this is a variable declaration for slices of type string. And it still works, so we can use this beautiful short form. Another way of creating a slice, and I'm just going to show it very shortly, is you can also write it like this. This is also a form of creating an empty slice. So we could write it like that. It's equivalent to the version above. And what this version can do for us is we can specify initial values like this. So I can write here 1 banana test. I can't do this with this statement, but in this case I can write initial values, and it's going to immediately create a new slice of size 3 with these initial elements, and I can still append things, read things, slice them, etc., etc. So yeah, 1 banana test. But for now, let's revert this and keep our make function there. So now we can apply all this knowledge to actually progress in our program. What we want to do is we want to store a slice of words. We already created it and appended the words and printed it. And let's look at our roadmap. We want to count the total number of words. So you already know how to do that. We simply use the lang function. So you can say total count of words, and that's our length function. Okay, 5,497 elements in the list. And just to illustrate it, of course, when I append elements or remove some of them, the size changes. So at the end, let's say we append the word and that is included. And now the size should increase by 1. And it is. Length returns 5,498. So that's it. Now you know the basics about lists or slices in Golang. Next, let us learn about how to read a little bit of text from the terminal input. Because what we want is we want to offer the user to enter a word, and we are going to look for the count of this specific word that the user entered. We can actually reuse our knowledge about scanners. We saw here that buff.io has a function useScanner, and it accepts a reader for creating it. And then the scanner handles the parsing of the input like we did here, specifying the split function with the predefined scan words function. So after we read all our words, we create a new scanner, and let's put this in a function to actually clean this up a little bit. It's always a good idea to keep your code nice and clean and readable. And what we extract there is the reading from the file and the returning of words. So we can call this read words from file. And we pass it the file name. And we return a slice of strings. And I'm just going to move it there so it's nicely encapsulated. And we need to use the return statement for terminating the function and returning our result value, which is the words slice. Now I can just redeclare a variable words here and assign the result from the function call. This is called input.txt, but careful, we have to make sure that the parameter we declared is actually used here. So otherwise it will always try to read input.txt no matter what I pass during the function call here. Now let's quickly check that it still works. And yeah, we got the total count of words. Let's create another function, and that is called read line from terminal. And it returns a string, which is the line that was read. We can just use the new scanner function. And the difference is we need to pass another reader. So while this reader was actually a buffered reader created from a file, we now want to read from the terminal. We can do that by using the standard constants defined in the OS package. So stdin stands for standard input, and that is the default input that you can use from your command line. So this is our scanner, and we do basically the same like below. We don't even have to specify the split function, because by default scanner splits after a new line, and that's exactly what we want. We can print helpful text for the user. That is enter word to search for, enter word to search count for, confirm with enter because that creates a new line. Okay, now we can say scanner.scan, and it will return true, if you remember correctly, once we read something. So we can immediately return our text. So scanner.text. If it returned false, it means an error occurred, or we are at the end. In our case, it's an error because we immediately return off the text after the first read. So we're not doing the same like here, like reading over and over again. We're just reading once, and the first line that we get is our text. So if it returns false on the first call, obviously there's nothing in there. We may have an error. So we can check if there's an error. can combine it like this. Not scanner, sorry. Error. And by separating these with a semicolon, you say, do this first, assign the error, and then we check it. If it's actually not nil, and that means we got an error. And in this case, we just want to print it for debugging purposes. Error on reading input. And then again, we want to, we could say we want to exit, but I guess we can do something else here. We can just say at the end, okay, if we didn't go here for reading the line, we can say return an empty text. That's valid too. And yeah, that's our form of error handling here. We already printed that something was wrong. So let's add the error handling below too. We already did it for the file opening. In theory, we could also get an error here during scanning our words. So error on reading words, we should add this since it's a good practice to think about how to handle errors. Otherwise, the user or you yourself for testing don't really know what's happening. Let's see if it actually works. We're just going to say read line from terminal, and we're going to call it input, print it. So that's %s for strings. Could also use v as the default format. Let's see if we can echo back what we typed. Enter words to search. Count for, okay, enter word, singular. And I'm going to enter milk. My input was milk, okay. I'm going to enter cheese. It's going to be cheese. If I just confirm with enter, we get the empty string because there was nothing but a new line. Okay, so now we know how to read one line from the terminal. Let's actually search for the word that we are looking for. So we get our list, or our slice, sorry, that is words. And of course, we don't know the indexes of the word we are looking for, so we need to search. We basically need to run over the complete slice and count the number of occurrences. So let's assume a count of 0 for the start. And we are going to iterate a for loop. So nothing fancy here. Length is our friend for the upper bound. And index plus plus. Now we have to check for every element if this is the word that we are looking for. So if it equals input, so we increase the count plus plus by 1, but we have to keep searching because there might be more of them, or there might be 0. So we need to look at every element, and at the end we can say that this is our count. And let's see if this works. Let's see how often we find the word milk. 28 times. So when you open your input.txt in an editor where it supports searching, you can look for milk, you find it 1 of 50. But remember, we are still looking on data that we didn't clean up. So the case is not respected, and there are a lot of special characters like commas here, or maybe a dot or something like that, that is still included in the word. Moreover, it counts things like milked. Can I say a match whole word? Okay. Now these are less, but it still doesn't match it because we didn't clean up our data. So let's pick something that is not so frequently written here. Let's look for etymology. Don't know if I'm pronouncing it right. I'm going to paste it across 2 times. Yeah, that's it. The caption and the entry in the table of contents. Post-Roman. It's probably also 2 times. Yeah, the caption and table of contents. And something like cheese, of course, will have a high count above 100. So that's how you search inside a slice, or you can apply the same principle for arrays. It's pretty simple, pretty straightforward. Just keep in mind that it's not very efficient if you have a very large list, or if you need to do this over and over again. We've managed to count the number of occurrences of a specific word, but as we already saw in my testing example, the results are quite messy because our words are not normalized and not cleaned. There are commas, dots, and so on. There's a mixed case, and that's why we get very messy results depending on the word. So now we're going to learn a little bit about common string operations and how we can clean up our input. There's a very handy standard package called strings. When you go to the Go documentation of this package, you will quickly find it and find a lot of documentation. There's all kinds of stuff here, like comparing, checking for prefixes, finding the index, so the position of a substring in a string, splitting strings. Yeah, that's to lower. That's what we can use for normalization. There are also other things like trimming, builder types that help you building large strings, readers from strings, and so on, and a lot of examples how you can use it. For example, there's a join function where you can concatenate values. So that's a slice of elements, of string elements, and by using strings.join you get a concatenated version. You can even pass a delimiter here, which is comma space, and you get this nice listing. Now, what do we want to do? Well, at first, as we already saw, we want to have a unique case of words, so we can actually look up the count without differentiating the case. So cheese written with an uppercase starting letter and cheese written in lowercase shall be the same word for us. So this and this, for example, for counting. So we import strings and we write a little function. Let's call it clean up words. That, you guessed it, gets a slice and returns a slice. Then we can make a slice. I will call it cleaned words. Make, pass the type, and we need the same size as the input slice. Then we're going to iterate as usual. We get the original word at position index. And now we want to clean it up. So at first, let's say strings to lower, and returns the string with all Unicode letters mapped to the lowercase. So by agreeing to hold all words as lowercase, we make sure that we treat mixed cases like the same word. And now the return value is the new word. So this is the individual word. This is the cleaned word. But we can reassign word. That's easier. Of course, it's the individual word here. And now we can say clean words at index assign a word. Okay. And finally, we need to return the cleaned words slice. Let's call this here, read words from file, and then we're going to immediately call clean words reassign, and then starting from that line, or after that line, we got the words variable initialized, reassigned with the cleaned up version. Let's see if this works. Look for cheese, 125, okay. And it grew because now we are counting all cheese instances. Now, one thing to note is when we enter cheese with an uppercase or completely uppercase, we're going to get count 0 because we are looking for lowercase, but of course the user may type in another case. So in order to make this work too, we have to do the same with our input in read line from terminal. So we are actually going to say scanner to text and wrap it in strings.toLower for normalizing. Scanner.text. normalize input for counting independently of case. And now it should work better. You can even write it like this. As long as the letters match, it works. So as you can see, the equals check for strings is case sensitive, and it will only yield true and therefore go into our branch when both match, including the case. So that's the minimal thing that we can do. What we also want to do is, let me show you by printing the word slice at the end. We need to remove commas and things like that. And as you can see here, there's quite a lot of stuff that's not really considered a word for us, like numbers, semicolons, mathematical signs, references to sources, dots, and so on. And we want to remove these things. So first I'm going to show you a simple, but yeah, let's say it's more like a quick and dirty way of cleaning this up by replacing these parts of the string. So in cleanup, in addition to lower, we're going to add more cleanup steps. We're going to say strings dot replace, and there you can specify the original string, then the part of the string that you want to replace, and the new string. You can do it n times or replace all. That's what we want to do. So the old string is word. We want to replace commas, so we enter a comma. And by specifying the empty string, we make sure that it basically disappears, the character of this part of the string. The empty string is a valid string, but it has length 0, so it is cut away. And of course, don't forget to reassign, otherwise you won't see any difference. And that's how we remove commas. So now you won't find any commas in here, but there's a lot of other stuff. So now to make this a little bit more complete, we can define a list or slice of values that we want to replace. I'm going to call this removable strings, and I'm going to use our initialization format, which looks like this, where I can immediately type the characters that we want to remove. We want to remove commas, dots, semicolons, what else? These brackets. We got some other braces, I guess. And let's see. The digits are a little bit more complicated. The percent signs and quotes. Now quotes, we need to escape them with a backslash, because otherwise the compiler can't distinguish it from the quotes that we just used to mark this as a string. So removable strings. And now instead of calling replace all 10,000 times, we can say for each string in removable strings, replace it. And that's where I want to tell you about another construct for iterating. And that is the range construct. It is basically a comfortable way to handle a loop. By using the range keyword, you get the index and the current element. We don't have to say index and iterate until here, increment. It automatically does that for us. And the beauty is we can immediately get the elements, so we don't have to say this. Now, since we're not interested in the index here, we use the underscore placeholder, which means I don't need that value, so I don't need a real variable. We can just ignore it. Because if you write it like this, it will be the index. So the first return value is the index, but we want the element. So we have to say ignore the first, take the second. Of course, if you only need the index, you can do it like this. So we could replace it up here, but also here we want the element. So let's actually simplify this like index comma word. And we don't need this stuff. We can just say range words. Gets incremented automatically for us, and we don't need this, right? Because word already holds the element. So pretty nice and simple. And now in a nested loop, we clean up the input word. Removable is my removable substring, and I state that I want to remove it, replace it with the empty string. And then it's reassigned so that we actually have the new value. So let's see if this looks a little bit cleaner. Still got our input. And yeah, it looks a little bit better. So as you can see, that's a mistake. There was a comma inside. We no longer have commas, semicolons, dots. There are still some things like minuses, colons, numbers. So as you can see, this is pretty tedious to do it for every do it like this, because you have to make sure you get everything that is not a word. So to make this a little bit more idiomatic and more robust, I'm going to quickly touch the subject of regular expressions. Regular expressions are a way of specifying patterns for strings. You can use it for matching, for finding certain elements, and so on. When we look for this in the documentation, we find very extensive things. And I think in Go it's called regexp. Yes, regexp implements regular expression search, and you can read a lot about it in the internet, not only for Go but in general. This is a pretty complicated topic in and of itself, but I just want to show you how such a task can be achieved more easily. So what we want to do is we want to replace again, but we want to use a pattern that is much better suited than what we did in a quick and dirty way. So we can actually say replace, pick the pattern, and then we have a cleaned up version. And there are multiple versions of it. We want the replace all string. So returns a copy of source replacing matches of the irregular expression with the replacement string. So we could even refer to submatches by using the dollar symbol. We don't even need that here. And this is the example. A regular expression is a pattern that you need to compile because it's some kind of language, as you might say. Although not as complex as a programming language, it's still pretty complex. And that is a pattern that says, we make this a bit larger. I'm looking for a substring that starts with A. Then there's an arbitrary number of X characters. The asterisk means arbitrary number, so it could be 0, 1, 2, 1000, whatever. And what follows is a B character. The parentheses are just for grouping this. And then by using the regular expression, as you can see in the output, the matches are replaced with T. So AXB is replaced. So this is replaced with T. And oops. And this too, because the asterisk means it can also occur 0 times. So it's just A and B and 0 asterisks. The minuses stay because they are not captured, not matched by this pattern. So don't worry if you don't get everything about regular expressions yet. I just want to give you a brief look at them. So let's import regexp and we will keep removable strings as a comparison. Let's just quick and dirty way is to use string replace multi-line comment, see regexp for simpler, or let's say for more efficient and robust solution. And we need to specify the pattern, that is must compile says give me a pattern, and I'm going to check if that actually compiles. We call it pattern, and regular expressions are powerful enough that we can exactly specify how a word should look like. we can say only alphabetical characters are considered a word by stating A to Z, sorry, in both cases. Actually, we can keep it to lowercase because we already called lower. By using that, we know it's a word. So this is a character class. The character class is enclosed in brackets. And inside you can list all characters that match. So I could write all characters of the alphabet and they would match. But a simpler way is to give it a range like A to Z. And that's basically it. There are much more complicated regular expressions which you can use to verify all kinds of things. You could verify if a Go program is valid, if an URL is valid, if an email address is valid. These are more complicated things. If you're interested in that, you can read tons of books and things about regular expressions. But let's just quickly see how powerful they are. We can say pattern dot replace all string. We pass the original string word. We pass the new string, which is the empty string, because we want to cut these characters away. And now we got our new word that we assign. Now one more problem. We said what matches are the word characters. So it will replace word characters. Let's actually see what happens. We want the opposite, but let's see. And as you can see, it's cutting away everything that is not a simple character of a word. So what remains are all these strange characters. Of course, we can negate that, and that's done with the with this accent circonflexe, as French people might say. By writing it in front, we say take the opposite, everything but these characters range are considered matching. And we can call it removable pattern. Now our result after saving should look much better. So what we still have here are a lot of characters. So there's still a mistake in there. Let's think about it for a moment. That was how we negated it. Okay, and you can see I probably placed it at the wrong location. So what we need to do is, yeah, place it inside. So as you can see, it's always helpful to look up how regular expressions work, and that's no problem. There are a lot of references out there, so you can always look that up. But by writing it inside, I make sure I'm negating this. So this looks much cleaner. Digits are out, numbers, special characters. What's still in there are very short strings like individual words. Here, as you can see, B, 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 B. These are not words, right? I would say for an English word, it usually has at least two characters like or be. The only exception from the top of my head is A, which has one character. So we will make a rule for that. We can say if it has at least 2 characters and the lang function comes in handy again, you can use it for strings. So you can read it here for arrays, for slices the number of elements, strings the number of bytes in V, which is for our simple cases sufficient. There's a difference between runes, as they are called in Go, characters in other languages, and bytes. But since we are only using A to Z, that's fine. We can say length needs to be bigger than 1 for us to consider the word. But there's an exception, which is A, and we're going to say bigger than 1, or remember our logical operator from tutorial 1, word is A. So if one of these conditions is true, we're going to add it to the slice of cleaned words. So either it has at least 2 bytes, so in our case it's 2 characters of the string, or it's the word A, we're going to add it, otherwise we're going to skip it. And now that even means we don't need such a large slice, but yeah, we can. It's not that dramatic that we couldn't keep it like this. Nevertheless, we can say create size 0, and instead we are going to use append. Don't forget this, because when you do it like this, you're going to get an error out of range. This slice has size 0. We want to append and grow it dynamically, so we say append clean words, reassign, and actually append the word. We no longer need the index, therefore we can do this again. And as you can see, this already looks much cleaner. We also had some blank spaces in there. As you can see here, these have also been removed by implementing the length minimum. So now we actually covered a lot of new things. You learned about the range construct. We had a brief look at regexes. Remember, this is a big topic in and of itself. Don't worry if you don't quite get it yet. Just remember that's an option to look into if you ever encounter such tasks. Now that we did some basic counting of an individual word that the user was looking for, and we did some cleanup of our input to get more accurate results by using some string and regex functions, let's have a look at our next feature on the list, which is counting the words for all words in the text, so counting the occurrences. I mean, what we're doing right now is we're just looking for occurrences once when the user enters the desired word. But actually it would be much nicer to pre-process the text and hold all occurrences of each unique word in memory, so that the user can enter as many words as he wants to search for, and we can quickly give him the count of the word. So in order to do that, I want to introduce the concept of a struct to you. Right now, we're only using a slice of strings for returning words, and we're using integers for holding the count of an individual word. Now, what we want is to store both things nicely together. We want to know the word and its count, and we want to do that for every unique word in the text. So a slice is a good idea for that, but at the moment it only holds one data type for us, which is not enough. So by using a struct, you can combine several parts of information and data types if you want to into a new composite type. It looks like this. You start with the type keyword, then you write a good name. We can use the name word stat for word statistic, and then you write struct. And inside the curly braces, you can define which kind of fields you need to describe this type. So in our case, we just need to hold the word, which is a string, and the count, which is an integer. You can, of course, add more fields, and that's how you compose new structured types. You can imagine it like some kind of bigger object or something like a building that you construct out of individual pieces. So it's a nice form to encapsulate data and to make it much more easy to program and to read. Now that we have this composite type, we can use it in a new function. So let's write a new function that counts all words. So count word occurrences, let's say. And we're going to return a slice, but this time it will have the type of our newly defined struct, so a slice of word stat. That's our return type. Now let's remove the counting up here, since we are going to replace it. And let's also remove this. And we put the input in a comment for now. So what we want to do then is call our new function, count word occurrences. Of course, we have to pass it the slice of words, because otherwise we don't have anything to search. So that's our parameter. And notice that words already refers to the cleaned up words here, because we reassign the return value. And then we got our word stats. We're getting another slice. I'm going to call it word stats. And I'm just assigning it here. Compiler is saying, okay, we don't use it yet. So let's simply print it, fmt.printf. We can say word stats. I'm using the default formatter %v, so we can have a look at how that looks like. And just to get a quick feedback for the minimal implementation, we're going to return an empty slice. So as you know, we can write it like this. You can use the slice notation the type of the elements, and then curly braces for an initializer. So save your program and go run main. As you can see, by default it's an empty slice as we wrote it, and that's how it's printed in the default formatter inside these brackets, no elements there. Now let's say we want to add some elements. First, let's extract a variable here. I'm going to use the explicit form to make it more clear, and I'm going to call it word stats. Calling make to allocate memory and passing the type as well as the size. We're going to use 0. That's good enough because we don't really know how many elements we're going to need because of multiple occurrences. And now just return it. So of course the type has no s at the end. Word stat. Okay. So that's the equivalent to what we wrote before. And let's say we now want to, just for testing, want to insert first element. Then I'm going to use append for appending it at the end of our empty slice. And reassign, of course. And now how do you create an element of type, of a struct type word stat? Well, you just write the type and use curly braces. It's very similar to, let's say, an initialized slice, as you can see. The curly braces mean it's created. You create an instance of this struct, but we are not setting any values. So let's see how this looks like after we saved. And we can see there's just a space, I guess, and a 0. And that's because we didn't initialize any values. Go uses the default values. The default value for string is the empty string, so we don't see anything because the empty string has a 0 length. And the default value for an integer is 0, so that's why we see the 0 here. Well, let's actually set some values. So first the word. I'm just going to pick a word from the top of my head here. Let's say cheese, and an occurrence of 17. So first value is the word, same order as here, and second value is the count, an integer. And of course this gives us a better representation. So inside our slice there's one element which is a struct containing cheese and 17. Pretty simple, isn't it? Now if you want to make this more explicit, you can also specify which fields you want to fill by writing the field name and a colon. This can be helpful sometimes, e.g. when your struct is pretty large and you don't want to get confused with all the fields, or maybe you just want to initialize parts of it, like let's say we're not interested in a word, of course we are, but just for demonstration purposes, then we have to say that 17 is the count, because otherwise the compiler doesn't know which field do you mean. It says it cannot use the int type because by default it assumes you are adhering to the order, and at position 1 there is a string. So that's why you have to specify the name in this case. Also, if you don't adhere to the order, you don't have to. Usually it's a good idea, but we could also swap the order here by stating the field names together with the values. So this works too. So now that we got that right, let's actually implement our counting. So what do we need to do? We need to process every word in our input slice. So for every word, look for other elements containing the same word and increment. So simply speaking, we need to use a loop for running over our words. Now we can use the range construct that I already explained in the cleanup words section. So you can say ignore the index, which is the first return value from range, and hold a word. So just as a quick refresher, the first return value of range is the current index, and the second the element. We're not interested in the index, that's why we can use this underscore to ignore it, but we're interested in the element, the current word. Now, for this word, we need to check if we already got it in our result list. So we need to iterate word stats. We're going to use the index here, and I will explain why in a minute. I'm going to call this stat and also use the range function. And now we need to actually check. So if our word equals stat.word, then we found it. I need to increment the count. Now, one thing to note here is that we need to compare word, which is a string, to stat.word, because our word stat slice contains struct types, our word stat struct type. So you can't just say compare with word. The compiler will complain because it cannot compare a string with a word stat type. It doesn't know how to do that, but it knows how to compare strings with strings, so this works. By using the dot notation, you refer to a specific field in the struct. Now we also got the index, and that is because we want to update our results slice, because we're now at the position where our existing word is present. So we can say word stats.index, that's our current position. And then we can say dot count, refer to this field, plus plus in order to increase it. So again, this is just the short form for doing this. And we're going to keep it at plus plus, as you know it from simple for loops where the index is incremented. And that basically increases the count of the stat that we already know and which matches the word. Now, what we still need to do is handle the case where the word is not present yet, which will be the case for every first occurrence, right? So somehow we have to remember, did we find the word or not? A simple way to do this is to add a Boolean variable. We're going to call it, let's call it found. I'm going to initialize the value to false. We're going to assume by default we didn't find it. So if we didn't find it, we can do something. We can say at the end of this for loop, okay, now for our current input word, we looked at every existing stat that we already know, we couldn't find it. So our Boolean variable found is still false. So that's why we have to check if not found. So exclamation mark. As you know, the condition needs to be true for the if branch to get executed. So we need to add first occurrence, right? Like, I mean, we have to create a fresh struct instance with count 1 because it's our first occurrence. And where do we have to set found? Well, exactly here. That's where we can set it to true, because if we found it here, we incremented the count. We know we don't have to create a fresh struct instance for the first count. But if we do, we can do it like this. Just use the append keyword, built-in function to add a new struct instance. And you can write it like this, as we already saw. Word stat curly braces. The word is our word variable, it's stored inside it, and the initial count is 1. Okay, let's see if this actually works. Maybe we did a mistake, let's see. Yeah, it did work. So that's our slice of structs. And as you can see, there's cheese, which has pretty high count of 167. And some other words. Some only have count 1. Some have more, like soft or brie, storage. So our basic counting works. One thing to note about this is that it's a pretty naive approach. So we have to keep in mind that during the counting we are doing quite some expensive work. We are running over all words that we get, and in a nested loop we are basically doing the same for all words that we already know. So when the input slice is very large, thousands or millions of words, which is possible with larger applications, this will become very slow, because then you have, let's say you have 1 million words, and that itself is not too bad. But for every of this million words, we are iterating our result slice, which grows continually. So at the beginning, this is empty, so this is not expensive. But it grows to, let's say, 500,000 words, and then 500,001 words, and so on. So basically multiplying this times length of word stats, which grows fast. So it's going to get pretty inefficient with large slices because it grows exponentially with the amount of steps that we need. What we can do to make it a little bit better, we can use another approach that we're going to learn about later in this tutorial. But for now, just remember this is a naive, simple approach that works fine for small slices and is a good learning exercise, but not a good idea for real production code. So let's write a comment here so that we remember that. Careful. This is a naive approach that is inefficient for large input slices, e.g. 1 million words, timeline words that grows fast and becomes slow to process. Okay. One thing I want to discuss too is that we have to use the index here to change the count of our word stats. You know, one could say, why index? We already got the element here in our stat. We can keep it simple by using underscore here and just say, okay, stat, I can access count, I can increment it. Isn't that simpler? Well, it looks simpler, but let's see if it actually works. As you can see, every word has count 1. Why is that? Well, you have to keep in mind that range, as a function, returns the index and a copy of the element in this structure. So what we get here is a copied struct instance. It's like when we create a new one and we insert the word and the count. So stat is a copy that is good for reading, but when we want to write it, we can increment the count of the copy, but that won't change the original element that is inside our slice. So we're just modifying the copy, not the original one. That's why we don't see it in the result. That's what you have to keep in mind for range. Since we want to modify the original element, we need to use access by index, and that is fine for us. And now we're back to our old implementation, which works nicely. Next thing we want to do is we got this handy slice of struct elements containing words and occurrences. And I already told you that slices have an ordered sequence of elements. So this is one of the defining characteristics of lists or slices, that elements are ordered. And there are some use cases where you can make good use of these characteristics. Just to give you an impression of what we can do, we want to sort the elements in our slice by the occurrence count, so that we have the words that occur very often at the top and descending down to the ones that occur the least, so only one time. Or if you want to see it the other way around, we can reverse the order too. So right now we got a very mixed slice. So you can see it when you run it, there's no real order inside. We're just counting in the order that we encounter the words, and that's basically how it's in the input text. So you can see cheese is at the top. It's very frequent in this text, but the fact that it's at the top is just due to it being the first word in our input text. So we're processing it in the order that we encounter the words. So the second word is from, as you can see here, the third Wikipedia, then the, and so on. So that's our current order. But we want to print it nicely from, let's say, highest or lowest to the other end of counts. What we need to do is we need to sort this slice. Now sorting is a subfield in and of itself in algorithms and computer programming. It's pretty popular also in teaching programming, but the detailed mechanics of sorting are maybe a topic for another tutorial. I just want to show you today how you can use standard library functions for achieving a goal of a sorted slice, because most of the time that's what you're going to do. Most programmers, although it is helpful to understand how sorting works in an implementation, it's not practical to implement it yourself every time because of efficiency and correctness. Basically all programming languages have standard libraries with sorting functions that are very good and solid. So, as I already showed in previous tutorials, you can go to package.go.dev and search for packages that you're interested in. You're going to get standard packages as a suggestion, or other packages that are maybe hosted on GitHub or other sites, but which can be found in the internet. So we're just going to type sort. And right at the top there's a standard library package called sort, which seems to contain functions that we're interested in. Again, there are several examples and there's an index that you can look into. There are several different ways of specifying sorting, because we have to tell the standard functions what the order is that we want and how to determine the order. So you have to know if an element is less, equal, or greater than another element, right? Because otherwise you can't determine the sort order. So that's what you have to program yourself in most cases. I want to show you one of the most simplest way to sort elements in a slice. And there is actually a function called slice. And when we go there, we can see, okay, that's the signature. So parameters, name of the function, return value, and it's expecting a slice x and a function less. So x can have any type. That's why it's called interface. This is the empty interface, which basically means you can use any type here. We can discuss this in detail in a later video. But more interesting for us is the function, which is a second parameter. Yes, Go allows parameters to be functions, so you can pass a function as a parameter to another function. And this function has two three parameters, right? Two parameters and one return value. So parameter I and j, these are the two elements that we want to compare during sorting. So imagine you sort a list of numbers by hand, then you would say, okay, is this number, my first number, is it smaller, equal or greater to the number at the next index? So I is one element and j is the next element that we need to compare. And bool, we can read it here. Bool says if I is less than j. That's why it's called less. So if I is for us has a smaller value than j, we are going to return true, otherwise false. And just by giving this type of information to the function, it can do the sorting for us. So let's look at the documentation example to better understand what's going on. You can see there's a slice that is defined here, and it's similar to ours in that it contains a string and a number, so a name and an age. Now the slice function is called sort.slice, so sort the slice. The slice itself is passed. Oh, I did some editing here, I didn't want to. The slice itself is passed, and then the function. That's just the header of the function that we already discussed. And here's the implementation in curly braces. So we have to check if the element at index I is smaller than the element at index j. So you can see I and j are indexes. We know the slice, so we can access the element at the index. And then what do we want to compare? Well, in this example, they are comparing the name. But you can also compare the age. So that's what you have to specify. It depends on what we want to compare. As you can see here in the output, when you pass the function that compares the name, you get it in an alphabetical order. Alice, Bob, Gopher, and Vera. And by age, you get the ascending order by age. Okay. Now that we got that, we can apply this knowledge to our program. So we get our slice of word stats and we want to sort it. We first need to import the sort package in order to use it. So add it to the import list. Then we can call sort.slice. This is the function that we just had a look at. We pass our slice, and now we have to define the function. So before I'm going to write the function in line, we can write it like a classical function, just to make it more clear. So let's write a function here. And we have to satisfy the parameter list in slice. So let's have a look at it. It has to look like this. I'm just going to copy it. So we got two integers, left and right, if you might say it so, and a Boolean return value. And the function is called less. Now you can change the names of the parameters and the function name, but we have to keep the types and the order for the compiler to know how to do its work. So we're going to name this is word stat less than. Yeah. And then we got the left index and the right index. And now, as you can see, Our problem here is we don't have access to the slice. We now need a way to access the slice because otherwise we can't access the elements at left index and right index. And that's where using functions as closures comes in handy. We can basically define this function right here, and we can access the enclosing, so we can access the scope on the outside, the variable, because here we can't access word stats. I'm going to show it to you. Word stats, what does the compiler say? Word stat is not an expression. Okay, let's say left index. We basically want this, right? So we want to say word at left index smaller than word stat right index dot word. So that would be fine if we would have access to word stat. But it says it's not a type. It's not a type because it can't see what we mean. We would need a variable like this, but that's a new variable. We want to use the one that we already have. Now we could pass it as a parameter, sure, but that would change our function type. And slice expects a function that has exactly these two parameters and this return value. So just to make it more clear, let's try this. Let's do it the naive way and say we got the slice here, word stats of type slice word stat. So now the compiler is happy in our function stats, but when we try to pass the function here, the compiler will actually complain. So passing a function like this is possible. You just have to use the name and not add the parentheses because that would be a function call. You just want to pass the name to the function. But in our case, it says cannot use value as func bool value in argument 2 because the types don't match. The type that we provide is a function with two integers and a slice of word stat return value bool. But the standard library function expects us to pass only two integers as parameters. So that's why this approach doesn't work here, although it could work in general. Instead, we can define the function here where we have access to word stats. I'm going to make this a little bit simpler for the beginning and say call this is word stat less than is now a variable that we assign our function that we define here inline. So it's actually like this. And now the beauty is we can access our slice word stats without passing it as a parameter. We can access it here because our function has access to the outer scope where these variables are defined. That can be pretty handy in a lot of programs when you use it for specific tasks. Now, what did I do here? Not only did we create a function inline inside our actual main function, we can also assign it to a variable because functions are, as they call it, first-class citizens in Go. So functions themselves are types together with the func keyword and the parameter list, including the return value, you have a type. So to make it more clear, it's getting really verbose now, but just to illustrate my point, we could write this. I could say this int bool. That is the very verbose expressive form. So I got a variable with this name. Its type is func, 2 ints as parameters, and a bool return value. So this is the actual type. And then I assign it the actual implementation of the function, which specifies the implementation details. Now we can pass that function. We can sort the slice and afterwards print it. So let's see if this actually works. So as you can see, the order is not quite right yet. Because why? Because I sorted by word. We ordered by the word, which creates an alphabetical order. So A is the first one and Z is the last one. So Capone, Zealand, Zinc, and so on. So let's fix this first. We want to order by count, not word. We can do that right here. Of course, both have to be the same type. And retry. And you can see the most common word is the, followed by cheese and the less common words that have only count 1 are right at the beginning, so it's ordered in an ascending way. Okay, that's already pretty nice. We can even simplify that. You know the shorthand version for declaration and initialization. So we can omit the type on the left side because the compiler is smart enough to figure it out by looking at the right side here. So this is our inline function for comparing elements needed to perform actual sorting. Since we need to specify our sort criteria. Okay. You could go even one step further and immediately write the function here. So I could avoid the extra variable and do it like this. So that's even shorter. Pass function. Note that we have access to enclosing variables like word stats. So that's the special thing about defining the function here. Now let's see if it still works. Yes, it does. Now what can you do if you want to reverse the order? Pretty simple, you probably guessed it. Instead of returning less than, we're just going to invert it and say return greater than. That's how you get the other way sorting. So rarest words at the bottom, most common words at the top. But I like the other way a little bit better since we immediately see the most common words at the bottom. Okay, that's how a simple sorting usage works. You have to specify the order criteria, and the standard function takes care of the actual sorting. If you're interested in sorting, just Google around, look for other videos. There's a lot of computer science stuff talking about sorting, how it can be implemented, different efficiencies. It's part of a lot of educational programs and studies. If you're interested in that, definitely check it out in detail. Okay, next we want to complete our little program by making the lookup of a word more efficient. So we recently introduced the concept of structs and slices, and we also learned how to sort them by a specific criteria. Now, going back a little, we already implemented a readline from terminal function, and then we counted the requested word and printed the occurrence count. Now, how can we improve this? I mean, right now we would need to search in our word stats slice like this. We would have to say iterate over our word stats slice, and if our current word, let's name it stat because it's our composite type, but if stat.name equals the input, we can say print the count. So stat name is obviously wrong, it needs to be stat word. That's the compiler coming to the rescue. And we can say, okay, we found it. Print our word. So word count is stat.count. Once we found it, we actually don't need to keep looking because we know that we have one entry per word. And that's one example where you can use the break keyword. Break means exit the current loop. So the outer for loop is exited when you call break. Sometimes this can be useful, like here. So let's try this and run go main and see what we can test. Okay, I'm going to enter cheese, and the program has to iterate over the slice to find one of the last entries and print the word count. Now this basically works, but there are simpler ways to look up these desired elements, and that's where I want to introduce the concept of a map to you. A map is basically another very basic data structure in all programming languages, and similar to a list. It can store a lot of values in a single variable. But instead of a simple ordered list, it stores values by a specific key. So as you can see here, this is an example, a very simple example of a map. You can imagine it like a table in a spreadsheet program actually. Your first column is the key column and the second column is the value column. And the nice thing about it is you can easily look up a value by its key. And that is pretty useful for our example because we got a word name and that is our key. And by using this key, we can look up the value. Value could be our word count. So that is one example of how to use a map. It's a very basic structure type. It's sometimes called hash table or something similar depending on the language. But in Go it's called a map. When you compare this to a slice or a list, obviously you ask yourself, when should I use a list or a slice and when should I use a map? Well, there are pretty basic criteria that you can compare with your requirements. Both can store multiple values, so that's not a real distinction. But one major distinction you already know is that slices and lists provide ordered elements. So if your program needs to rely on the order of the elements, like when you're sorting or when you're printing output for the user and it shall appear in the same order that the user entered the data, then you probably want a slice. Maps are usually not ordered. That's also the case for the standard built-in type map in Golang. Some programming languages have different implementations for maps. Well, there's also possible to have an ordered map, but that's an advanced topic. If you want an efficient lookup, like in our example here, you would prefer a map because all you have to do is think about a suitable key and you can easily look up a value by its key. As we will see soon, it is much simpler to use and also more efficient in terms of the computing time that is required to actually find a value. Because as we already saw, if there's no such lookup mechanism, you basically have to search your slice. And when you get thousands and thousands or millions of entries, this can become quite slow, especially when you're nesting loops inside, because it grows exponentially in terms of the required processing steps. Another distinction to make is that lists are able to store duplicated elements. So it's not the case for our implementation right now, but you could store maybe names in it, names of persons, and you could easily have duplicates in it, like the name Bob appearing multiple times. That's not an issue, and sometimes you want that. Other times you want to make sure that there's only one element per value inside it. You can achieve that by choosing a suitable key. So in terms of words, our key would obviously be the word itself, and the value could be the count or some other statistic. There can only be one entry per word. So when I try to insert another word like flavor in our example, there will be no second entry with flavor. I can replace this entry, maybe by assigning flavor free, then it would get replaced. I could also delete the entry, but I cannot add another entry with the same name. So that can be pretty useful. These are the major differences between maps and slices or lists that you can keep in mind for choosing what to use. There are some more differences also on a finer grained level, but these are the basics. So now that you know, a map is just a very simple lookup table consisting of two columns. We can jump into our code and see how we can apply this knowledge. So we already got our slice of word stats. We also got our input from the terminal. Now instead of searching, we can easily look up by using a map. But first, we have to construct our map. Let's convert our word stat slice to a map by writing a new function. We can call it stat slice to map and pass it the slice. We're going to return a map, and you declare that by writing map, then brackets with the key type. In our case it will be string because the key shall be the word, and our value shall be the count, so an int. That's what you append right behind the brackets. So we need to create a new map first, and I'm going to name this map word to count. You can give it any name that you find easy to read and good to remember. I usually like to name maps with the key to value type. So by naming it word to count, I can easily see by means of the name that it maps word keys to count values that can be helpful to remember the purpose. And now I'm again using the explicit declaration and initialization for illustration purposes. You can see that make is our friend here too, and it allocates a new fresh map for us by specifying the type. Now we can iterate our input slice. Don't need the index, just use the values. Stats. And we need to fill the map. So that's done by using the bracket notation. I can say word to count. Now I pass the key, which is word, and I assign the value using the assignment operator, which is actually it's a struct type, so let's call this stat instead of word. And if you paid attention, you know I have to call stat.word to actually get the string. And we want to use stat.count as the value. And that's basically it. We can return the map. So for every word, we created an entry in the map with the count. Pretty simple, isn't it? We just converted a slice to a map. Now we can use it here. We can call the function, pass our word stats, and I'm going to assign word to count. Here you can say you can use the shorthand declaration and initialization, as usual. Then we're going to read the input. And now it becomes very easy. We know what the user wants to look up. We can call word to count with the key, which is input in this case. That's the word that the user is looking for, and assign it a variable. Now the first variable is the actual stat that we are looking for. Declare and initialize. And there's also a second value that is returned that can be used to check if we actually found something. So I'm going to name it found. That will be true if the key value pair is present in the map, otherwise it will be false. And we can use that to say if found print f our word count found it, and then stat, it's not the stat, it's the count actually, count, else we can write word is not present. Okay. So, pretty simple. It's easy to look up the value in the map and easy to check if we actually found it. We don't have to search for it. It's easier to use and more efficient for a large number of values. Let's see if this works as expected. And look up the word. I'm going to use cheese. Found it, word count 167. Yeah. And if I enter unknown, it's probably not there. Oh, unknown is actually there, okay. Word count 1. Let's use something that is not there. Maybe alien is probably not there. Yeah, word is not present. So as you can see, it works beautifully without having to search the word. What else can you do with maps? Well, it's pretty easy to replace values because there's only one entry per key. That is a property that we could use during counting. So as you remember, count word occurrences is our naive implementation approach. We use searching for that. We can use our knowledge about maps to improve upon it and write a more efficient implementation. Not only more efficient, but also more simple. So let's do this. First, let's rename this to count word occurrences slow, just so that we remember which implementation is which. And I'm going to copy the function header and name it count word occurrences fast. So where do we call it? Here. And that's before sorting, right? So actually we need a slice there to be able to sort. Sorting maps is not possible. Therefore, I'm going to put the sorting in a comment just as a documentation, but I'm going to deactivate it. Just assume we don't want to do this here. Note that sorting elements in a map is not possible. Therefore, deactivate it right now. Okay, and here we're going to call count word occurrences fast. Then we won't need the slice to map call. And instead we are immediately going to use a map to determine the count. So word to count there. Okay. Count word occurrences fast obviously needs to return a map with key type string, value type int. And I'm going to show you the alternative initialization of a map, and that is without make, or without calling make explicitly. We're going to write the type map string int and use curly braces. So that actually means create a new empty map. It's very similar to what we saw for slices. The useful thing here is we could initialize the map with default values. I could write cheese by default, key colon value, as count 5 and milk 3. So that's not what we need here, but you could do that by using this notation. Now we're going to iterate the input slice as usual. Using our range function. And in our naive implementation, we had to start searching in our result slice, right? Because we needed to know if we already saw that value. Here we can say, okay, check our word to count map, look up word, and we can see if it already exists. That is the count. If it does exist, we already get a count. We can use the second return value in order to check if it exists. So if found is true in this case, we can say, okay, word to count word, assign a new value, and that is count plus 1. Because we already know that word, we have to increase the count. Else, if we don't know that word, we put the initial value there, and that is 1. Word to count word, assign 1. Pretty simple, isn't it? Now we just need to return the result map, and let's see if this works. We call it up here, that's our map, and then we look up the existence, save and run. Okay, let's look up cheese, found at word count 167. Let's look up juice, found at word count 3. Let's look up goat, 3. Okay, I think you get the idea. And of course, if it doesn't exist, like alien, word is not present. Yeah. So as you can see, when you compare it, count word occurrences fast, not only is it faster, which we're going to see soon, it's also simpler to read and write. because I don't need this nested loop thing. Checking if the word is already known is much easier with a map, and the whole thing is much more elegant. So just keep in mind, maps are good for lookup by a key, and you can easily check if there's already an entry. We can update entries and get them by using the bracket notation specifying the key. And the assignment is always the value. Now the key and the value type can also be different. You always have to think carefully about which key makes sense. But the value could also be, let's say, our struct type. We could also create our struct type, and then we could store much more values in the value of the map. But in our case, the count is sufficient, so we can keep it simple here. Last thing we want to do in this tutorial before our program is complete is we want to have a quick look at how the approach to finding word occurrences reflects in the program runtime. So since computers nowadays are pretty fast and our input data is not particularly huge, we also got a quick result by using our naive approach. But for larger input, this can be quite different. And when you encounter such a situation in a bigger program that's slow, or when you want to compare approaches to make sure they are scaling well and fast enough, one important practical thing to do is start measuring. There are a lot of theoretical concepts around processing efficiency, big O notation, and so on. That is definitely useful, and I recommend you look into that a little. But at the end of the day, it always helps to make a measurement and get practical results about how long certain data processing takes if you suspect it's too slow or if you experience this in testing or production. So let's deactivate the lookup part, and we're just going to measure the actual counting. So the approach search and increment in a slice versus lookup and increment in a map. That's what we are going to do. So at first, let's use count word occurrences slow, and we get our word stats as a result, which is a slice. Let's just name this slice result. And in order to see that it works, we are going to print it result. Okay. Quickly check that it runs. Yeah, it does. So there's no sorting in here, as you can see. It's just counting the occurrences per word. And now we need to find out how to do a simple measurement. You can imagine that we want to start a stopwatch at the beginning or in front of the process that we want to measure, and at the end. So in this case, we want to start measuring here and stop measuring there. Then we got a time duration and can print the duration for counting words. As always, the Go standard library is your friend most of the time. We can look for existing solutions. So there's probably a standard Go package, maybe time. Yes, it is. Time standard library. And there you can read about how to measure time. Time.now takes a current time, and by subtracting we get the elapsed time. There's also some other functionality. There's an example for duration. Yeah, and that's already an example on how to measure expensive calls. So time.now returns the current time, and by subtracting the later time minus the earlier time, you get a duration, which is our measurement. So we need to import the time package. Let's do this. Yeah. Then we're going to call time.now. So that's our start. It's actually returning a time value, as you can see here. And end time.now. And then we can say duration is end sub for subtract our second time, and as you can see it's returning a duration, which is the delta of time that has passed. And now we can print the duration for counting. I'm going to use the default formatter. That is probably going to include the time unit. So let's save and execute. And as you can see, duration for counting 15.51 and so on milliseconds. So pretty fast, right? Although we're using the naive approach right now, this is still pretty fast. But you have to remember that our Wikipedia article is not that big. It's for a computer program, it's just a few words. So let's repeat this a few times. So this time it's 20 milliseconds, 17, 16, 16, 17. So there's some deviation in it. It's not exactly the same every time, but that's roughly the duration that we can expect with such an input size. So let's create a file that is a bit larger. I'm going to copy the input file. I'm going to call it larger input txt. And we're going to just take the whole text, go to the end, and paste it so we multiply the content. So 2, 3, 4, 5. I copied it 4 times. Now we have about 5 times this size. You can quickly verify that. I'm just going to count the new lines, 428 lines in the original input, and larger input has 5 times the amount of lines. So let's see how this scales to our program. Make sure it's saved. And now we are going to pass input, larger input, because we have to make sure that we're actually using the larger file. And as you can see, it took a bit longer. Still pretty fast, but 128 milliseconds, 129. So that's a bit more than 5 times, right? 5 times would be about 100 milliseconds. So it's a bit scaling a bit slower. Not much, because it's still not much data, but as you can see, it's not quite linear scale. Now to compare that, let's switch to count occurrences fast. And this is our map result that we are going to print. So first, we're going to use the standard input file, save and run, and it prints our map. You can see that it's key value pairs. No struct in there, but just string to integer. And it's already much faster. It's just 1.4 milliseconds. Yeah. So that's about, oh, we're now in the microsecond range. 2 milliseconds, okay. So that's already 10 to 20 times faster than the slice approach with our standard input. Now let's see how it performs for the large input. Larger input. And as you can see, there's just a slight increase. We increased the number of lines and the size of the file by a factor of 5. But the duration for counting only about doubled. So now it's 2 point something milliseconds instead of 1. We're no longer in the microsecond range, some runs, but it scaled pretty well, right? 5 times the size and only 2 times the lookup speed. And it's still about 5 to 10 times faster than the slice implementation with the small input. And we are looking at 50 times faster, 50 to 60 times faster compared to the slice implementation with the same larger input file. So that already scales much better than the slice approach. Yeah, so that's basically it. Why does it scale better? Well, the map is just designed for that use case. You have a key that is hashed to a numerical value by using a hash function. And the data structure lookup can be performed in almost linear time. So it doesn't matter if I'm looking for the word cheese or the word milk. Since this is our key, lookup will take the same, almost the same amount of time. But when I'm checking our slice for the word, I have to iterate the complete slice to find it. And that's what becomes expensive the more elements I have, especially since it's a nested loop. So it grows exponentially. And this is where all this time is lost. If you're interested in that, feel free to do your own measurements, read something about the efficiency of data structure operations and big O notation maybe. Keep in mind that data structures are designed with different trade-offs. So that doesn't mean that slices are bad, Slices are very useful, but they are designed for other things in contrast to maps. The disadvantage of a map is I can't use it for sorting. As you can see here, we had to deactivate it. In a slice, I can sort my results for, maybe a nice displaying of the data for the user. Also, I may not care about the lookup of individual values. Maybe I just want to have a sequence of values for printing or for processing them later. So it's always a trade-off, and you have to think about your requirements, about which data structure makes sense for you. You can also use different data structures for different purposes. It's perfectly fine to use a slice when you need the ordering, like here, when you need sorting and pretty output. And then for lookup, we can use the map. That's perfectly fine. Keep that in mind when thinking about the decision whether to use a slice or a map. Now, one thing I want to state at the end is we're reading files, and one thing you should keep in mind when working with files is that files are resources that the operating system takes care of. And such resources should be closed and released once you no longer need them. So that's why in pretty much every programming languages you should close a file handle after you're done with it. So you can call file.close, which closes the file, rendering it unusable. So you should do it only when you're done with the content. We pass the string and we can return it. We don't need the file access anymore. And this makes sure that the operating system can clean up the file handle and basically clean up resources. You won't realize it when you quickly terminate a program like we do, but when you're opening a lot of files and when your program keeps running, maybe it's a network application or web server, the operating system could run out of file handles and your program will get errors at some point. So at the end, once we read the content, we want to call file close, and you can see it still works. Now, a best practice here is to actually not write this naively at the end, but after you opened the file, you can say defer file.close. And what defer does is it says, when you exit this function, perform this cleanup work for me, file.close. And the beauty about that is you can schedule this immediately after you got the file, so you don't forget it later. And I can immediately read it here. Okay, we thought about closing the file, but the program makes sure it only happens at the end of the function when this is exited. So it's not immediately closed, but at the end of the function when we no longer need it. You can verify that here. That's how it happens. Actually, we can we do a block here? No, we can't, but we could call a function. Okay, but that's a topic for another time. One additional advantage is that this is called in any case. So you have to keep in mind that an error might occur, like here during scanning. And in this case, we also want to make sure that the file is closed in every case. So it doesn't matter if it's a happy case or an error case, we want to close the file handle to clean up for the operating system. So that's another reason why defer is very practical. Defer ensures that your cleanup call is performed before exiting the function, even if an error occurs. Use it to release system resources after usage. Okay, that's it when working with files. Now, this is our complete program. We covered a lot. We talked about how to simply read file content. We introduced ourselves to the concept of lists or slices in Golang. We did some string cleanup work, had a brief look at regular expressions and simple string functions, and also did some measuring, especially when working with our second data structure, which is a map. Both slices and maps are very useful. Also remember we had a look at struct types, which is a very simple and elegant concept to create composite types and nicely encapsulate fields and values that belong together. Yeah, so that's our program. Feel free to tell me what you think about this tutorial, what you want to see next, what you like, what you didn't like. If you have any questions, put them in the comments. And as always, I recommend that you take action. Please do not just consume this tutorial and then forget about it, but try to program this yourself. Either do it alongside with the video, you can pause it at any time, or after the video you could also jump to individual chapters and try the bits and pieces that you're interested in. There are lots of opportunities to improve this program or to tinker a little bit with it to try something else. So, see you next time.